Bismillahirrahmanirrahim. Today's topic is normal distribution. Normal distribution is a distribution which is of continuous type and based on the continuous variable. Before going to the normal distribution, we will study about the two types of distribution. First one is the variable which is of discrete type, and this we have studied two distributions. This is binomial distribution and hypergeometric distribution. Both are discrete distributions based on the variable of discrete type, and its function is called probability mass function, and range depends on the isolated values of the x. And for the continuous distribution, continuous variable is considered, and these distributions are called continuous distributions, whose range starts from between two intervals a to b or any specified value. So first one continuous distribution we are going to study is called normal distribution. It's similarly we have the density the function in the binomial distribution, which is if you remember, it's f of x is equal to ncx p raised to power x q raised to power n minus x. The dense and that function was called probability mass function. Here in the normal distribution, the function is called probability density function. So come to the density function of the normal distribution. This is our probability density function of the normal distribution. F of x is used to denote any density function. Generally, it is used for all type of distributions. So f of x is equal to 1 over sigma under root 2 pi e raised to the power minus 1 by 2 x minus mu whole over sigma whole square. So this is the density function of the normal distribution, which involves variable x here. So range of x is always written with comma, and range is minus infinity to plus infinity. X is of continuous type, that's why two values minus infinity and plus infinity are given, and in between all the points on the number line are included in this range. So parameters. The normal distribution have two parameters, mu and sigma square. Mu is its mean and sigma square is its variance. And normally we use x with tilde sign. It means x follows, n stands for normal distribution. So x follows normal distribution. Within parentheses, we write here the parameters of the distribution. Its parameters are mu and sigma square. That's why we have written in parentheses mu and sigma square. So we are talking about the random variable, the variable, so it should be in capital uppercase. So x follows normal distribution with mean, mu, and variance sigma square. So this is the normal distribution. Come to the probability density function. This is density function x. If we put any specified value of x here, then that specified value comes here, and parameters are given mu and sigma square. If we put all three values here, numeric values here, we can solve this expression and also multiply this expression. Sigma is given, mu is given, and at x any specified point, we can calculate this value. At any specified point, that value is called ordinate. Now come to the figure and I will tell you what is meant by ordinate. So at x is equal to x naught is any specified value, and f of x naught is its ordinate at the point of x naught. So the shape of the normal distribution is bell shape. You can see there are three shapes of similar, three bell shapes of similar type, but they are slipped away on the along with the x-axis. First one is blue, and next is the orange one, and next one is the green one. So in this figure, this is also normal distribution. Second one is also normal distribution. Third one is also normal distribution. All three are the normal distributions. But what is the difference between this? If you see the peak points in each figure, these are the peak points. If we locate, if we uh, point out an horizontal line along the x-axis, along the y-axis from peak, from here up to this point. Similarly here, from peak to this point. These are the parallel lines to the y-axis. So this is again the peak of the third figure. So you can see that a peak having the same value, peak having the same value, and which this value is, if you can read, 0.25, and next is if each is 0.22, then this is 0.27, 0.28, similar like this. This is the 0.28. So height of each shape is 0.28, and the point on the x-axis are different. For example, if I write here, this point is -1, this point is here +1, and this is 1, and height is 0.28. 0.28. 0.28 is actually ordinate, okay, at specific point. This specific point for the blue distribution is -1. So we can write it as, this is f of -1. This is the specified value. Is equal to 0.28. For the orange distribution, height is again 0.28, but now function is 1. Here the parameters are different. Its parameters are mu is equal to, mu always lies in the center of the distribution. So this is mu of the first distribution. This is the mu of the second distribution. And this is the mu of third distribution. So mu are different, but sigma is the shape parameter. So sigma is same. That's why I am mentioning here, sigma is same. For all three distributions, sigma is same, but mu is different. Okay, so in each distribution, mu is different. So mu is equal to -1. Similarly, for this distribution, again, height is same. So ordinate is specified value of any point on the curve. Not only at the peak ordinate exists, all the points here on the curve I'm just pointing few points. So many points between these mentioned points exist. In all these points, for example, these one. And for all these points, we have ordinates. On all these points, we have ordinates. Okay, so at every point of x, this is our x. For every point on x-axis, this is our x naught. Any point on x-axis is called x naught. So at every point, the height is called the ordinate. So this is our ordinate. This point, this height is called ordinate. F of x naught. This point is called f of x naught. For specified values of mu and sigmas here. Remember, mu is different for each distribution and sigma is same. I think now it's clear what is meant by the previous slide, the ordinate. So in the previous slide, we have studied ordinate. This one. Let me clear up all the annotations so that you can view clearly. Good. This is your ordinate at specific point. Come to the next figure, which is this one, in which sigma is different, but one thing is same. Mu is same and sigma is different. Mu is same, that's why we can see that all shapes of the normal curve starts from the different points, but the center of each distribution exists on the same point. All peaks exist in the same point, and that same point is called its mu. So mu is 10 for each distribution. Mu is equal to 10 for each distribution. Mu is equal to 10. But it's longer tail, longer height, it's lactocartic. Center one is mesocartic, and third one is platycartic. You can say that it's flattened as compared to the center one and the first one. So three different shapes you can see here in this figure, and that's why I mentioned here mu is same, which is 10, and sigma in each shape is different. So this is another property of the normal distribution. Now we will move to the next slide, in which we discuss its properties. Property. First property is the total area under the curve is 1. So this is the distribution of the normal curve. This is a normal curve, normal distribution. You can see it starts from -6 and up to the +6. So the gray area under this curve is 1. Every distribution of the normal curve have total area under the curve is always equal to 1. Similarly, like we have done in the binomial distribution, we calculated the This is different probabilities at the points x, and write in the table form, and then take the sum of all these values, and sum should be equal to 1. So sum of all probabilities in the discrete distribution is equal to 1. Similarly, in the continuous distribution, the total area under the curve is 1. Area is here, if I can say that area and probability are the same. The word probability and the word area are same here. So we can write it as probability, sum of probabilities is equal to 1, or either the total area under the curve is 1. So this is the first property. And the second property is probability from minus infinity to plus infinity. You know very well that this point on the left side is going to a point minus infinity. So minus infinity exists here, and the point, if we extend x-axis on the right side, it goes to the point plus infinity. So if we extend this curve on both edges, the total area between these 2 points under the curve is 1. But if we draw a line here from the peak ordinate at the point mu, as you know that the mu exists here under the highest point. So mu here is 2. So we can write it as mu is equal to 2. So if we shade the area before the mu, which is this one, I'm just trying to shape the area. Actually, shape is very small. This area. So this area is center point is called mu, and area below this point is shaded here. So if I write here, this is our mu. And the area from minus infinity to mu is half. Half mean 1 by 2 or equal to 0.5. So this is minus infinity to mu. That's why area is minus infinity to mu, and equal to 1 by 2 or 0.5. So half area exists here. This is 0.5. Below the mean, below the mu, this is 0.5. And half area, if I color it in different shade, then this is the area which is exist on the upper side of mu. Okay, I'm just trying to shade this area and differentiate it from the blue color. So all the area above this point mu is again, sorry, it's going beyond this line. So this area is also 0.5. So 0.5 plus 0.5 is equal to 1. So total area is 1, and above mu is 0.5. Below mu is 0.5, above mu is 0.5. And if we take the total interval from minus infinity to plus infinity, the area is 1. By adding these 2 points, we can get 0.5. 0.5 is equal to 1. The next is the property of the bell-shaped distribution. You can see that the shape of this distribution is bell-shaped distribution, and it's looking like a bell. If you have seen the bell which are of traditional type, having this one. If you ring it by touching this pendulum with the edges, that it sounds. So this is actually the bell hanging with anything. So our normal distribution is similar to this bell. That's why the third property is its bell-shaped distribution. Its mean, median, mode, all are equal. Since we have done that mu exists in the center, so this is mu, and therefore we can see mean is here, x bar is your mean, so we can say mean is in the center, median is denoted by x tilde sign, so we can write here median is here, and also mode is here, which is represented by x hat. So all three values, mean, median, mode, are equal to mu. And mu is here 2, which is the point at under the curve at the peak. So this point. So mean, median, mode all are equal. Now come to the next page of the book, in which we will take up the points from the book. This one. This is the normal distribution. These are the three different points which are mentioning here the importance of the distribution. So you can say these 3 points are actually tell you about the importance of the normal distribution. As you know that in daily routine, we will deal so many values, so many observations, so many measurements. And from these measurements, if we specify, most of them are of continuous type. For example, weights of the individuals. For example, heights of the individuals. For example, IQ scores. For example, time, volume, distance, temperature, all are the variables of continuous type. If variable is of continuous type, then normal random variable is appropriate to find the probabilities. So normal distribution would be applied on those type of variables. So it's an appropriate distribution for such variables. Second is, it is the limiting form of many other probability laws. It's you can say that as in the size of the sample size increasing, limiting form means if sample size increases, all probability loss approaches to the normal. So it's now I think beyond to your understanding. So I'm leaving these 2 points for future, because in the 11.6 we will study the limiting behavior and the centered limit theorem. All these points we will take up in next chapter, inshallah. And the next topic is here, the next point which is mentioning here in this, sorry, this one. Normal probability distribution, in which this is your density function. I mentioned you in the presentation that fx is equal to this one, and mm, So this is a density function along with the range of the x, where x follows normal distribution with mean, mu, and variance sigma square. Uh, Next is the shape of the distribution. This is bell-shaped distribution. We have seen this shape properly. Next is these two figures. We studied it. Sigma is different for these two or three types of distribution. We can study it in such a way that you can understand it better way. First one is the density function. These are the parameters of the distribution. If we draw the PDF, for example, this one, if you can see, sigma is for all three distribution are same, and which is 1.5. You can see I've taken sigma here as 1.5. So sigma is in all three figures is 1.5. I'm just reducing it so that you can see values of the parameters as well as the shapes. This is sigma, which is 1.5. Mu is taken as -1, +1, and 2. First one is -1. Second one is +1. And this one is +1. Draw a line. This is +1. So this is, you can see, this is +1. And third one is 2. And 2 is now here. And first one is -1. You can see its shape is from here up to the point on x-axis under the peak is always mu. So you can see these points are called mu for each distribution. This is mu, this is mu of this distribution, and this is mu of this distribution. So now come to the next figure, in which we can mention different values of, for example, this one. If I'm taking mu is equal to 2, same one, and sigma as first one is, if, for example, 0.7. Next I'm taking 1.2. Third one is 1.7. Okay. And if I run this command, you can see different shapes of the curve, and all the peaks of the curves are on the same point. If I draw line on these points, so all these points are touches the same. So in this figure, you can see that the sigma is different. Sigma is different for all three types of shapes. Sigma is different, but mu is same. So this is our mu, which is same for all three shapes. Mu is equal to 2. It ranges from -infinity to +infinity. That's why I have taken -7 to +7, because all the pictures, all the shapes vanishes or touches x-axis. That's why it goes up to 0 ordinate. That's why I have taken these points minus. You can take -8 to +8, but if you are taking -infinity to +infinity, actually you will have a very small figures over the whole range of x. So now come to the book again, and we will see what are the next points. So we have done this. Properties First one is its continuous distribution. We have done total area under the curve is 1. Mode and maximum ordinate is this one. We can calculate it by this one. This is the density function of the normal curve. You can see that there is a point mu is mentioning here. In the density function, it was x, and x is replaced by mu. Since x is equal to mu. At this point, by substituting this point here in the density function, you can have mu minus mu. By cancelling out, you will have 0 here. E raised to power 0 is equal to 1. So all this portion vanishes, equal to 1. So you have 1 over sigma under root 2 pi. This one. If you calculate this numerically by substituting the value of sigma in it, you can have the maximum ordinate, the value of maximum ordinate. We can do this by the software. First one we mentioned here, the density function, probability density function of normal curve. This is probability density function of the normal curve. F is equal to this one. We can write it e raised to the power or exponent raised to the power, same way. And if you take this density function and substitute x here in a specified value of x, for example, I'm just copying it here, Control C. This one is now if I take sigma is equal to, for example, 2, and mu is equal to, for example, 5, and now these are the two parameters, and after substituting these two values, and x is equal to maximum ordinate exists at mu. We have seen that peak exists at mu, so x is equal to 5. If we take these points here, then the value of maximum ordinate is equal to this one, 1 over 2. You have seen that sigma is replaced here. Sigma is 2, so sigma is putting in whole this equation. Mu is also substituting in this equation. And at the point of 5, so substituting 5 here, you can have all these values. If we want to calculate it numerically, we can get the value in decimal form, which is equal to 0.199471. So in either way, you can have the value by substituting it, or you can study it by the figure. If I plot these values in the figure, for example, if I take this one and substitute sigma is only 2. Okay. There is, I think, some error. Mm, okay, leaving for the future. Now come to the point in our book. Maximum ordinate exists at this point, and its value was 0.19 something. It's a symmetrical distribution. Both sides, right hand side and left hand side, are equal. So mean, median, mode are equal. And its lower quartile is denoted by Q1 or x 0.25. Upper quartile is x is equal to 0.75, Q3. Both points, if I draw the figure here along with this property, then you can see this is our bell-shaped distribution. This is your x-axis. In the center, you will have mean, median, mode, and second quartile. Also Q2. Q2 is your second quartile. And second quartile is also known as median. So median is here. That's why I have written it here Q1, Q2. So if you divide the whole portion into four equal parts, then one line will be here and the third is here. So each portion, this one, this one, this one, and this one, all are equal to 0.5, 0.25, sorry, 0.25. Four quarters. These are the four equal parts. So each of the portion is of 0.25. And if add up all these 4.25, 0.25, 0.25, and 0.25, it will come up with 1. So first line is called, this is Q1. This is your first quartile. At this point, your first quartile exists. Q1. This is your Q1. And this point at the end of the third line is called, this is your Q3. This is your Q3. So, taking the eraser. Okay. Q. This is your Q3. Okay. So the difference between this point Q2 to Q3. So this distance is same. If I shade it using different color, for example, this one. This is your area from Q3 and from mean to Q3. This one. This area is equal to the area if I will shade beyond this line. For example, this one, the area, this one, yellow color, are same. So this is your second problem. And third is all odd order moments are equal to zero. Thank you for today. Up till now, we have studied four properties. Inshallah, in the next class, we will study the remaining one. Thank you so much. Allah Hafiz.